Just look at any refinery or chemical plant, and you'll see them, these massive, towering structures. They're the real workhorses, the engines driving production. But let's be real, anything involving that much fire on that scale, well, it comes with some huge challenges, from mind-boggling operational costs to really serious safety hazards.
And when we talk about costs, we're not kidding. The scale is just staggering. Get this. Fired heaters are the single biggest energy hog in the entire manufacturing sector. They account for a massive 37% of all energy used. This picture right here just perfectly shows why even a tiny improvement in efficiency can translate into millions and millions of dollars in savings.
So when you think about it, operators are really juggling four big things all at once. First off, you've got to run safely and stay on the right side of all the environmental rules. Then, you're constantly battling inefficiency that's just burning through fuel and money. You also have to think about the long-term health of the heater itself. And all of this, all of it, hinges on the skill of the operator, which, as you can imagine, can be a huge variable. Okay, so to really get a grip on those challenges, we've got to go back to basics, back to the design of the heater itself. And it all starts with one core concept: draft. Basically, how the heater breathes. So what is draft? Think of it like a gentle, controlled vacuum. The pressure inside that firebox is just a little bit lower than the air pressure outside. It's that tiny pressure difference that literally pulls the fresh air in for the fire and then pushes all the hot exhaust gas up and out the stack. Simple, right? No draft, no fire.
All right, so the simplest kind, the one you see on the left there, is a natural draft heater. It works on a super simple principle we all learned in science class: hot air rises. The sheer buoyancy of that hot exhaust gas creates the negative pressure all by itself. Now on the right, that's a forced draft heater. This is where we get a bit more control. We're using a fan to actually force the combustion air right into the burners.
Now, building on that idea, we've got two more advanced types. The induced draft heater, on the left, sticks a fan near the stack at the exit to pull or induce the flow right through the system. And then, on the right, you've got the whole shebang, a balanced draft system. This is the top-tier setup. It uses two fans, one pushing air in, one pulling gas out. It gives you total, precise control over the pressure inside. So knowing the design is one thing, but actually running it, that's a whole different ballgame. Now let's talk about the levers the operators are pulling every single second to keep these things running safe and sound. Now, this is where it gets really interesting. There's this fundamental conflict baked right into the physics of it. The perfect mix of air and fuel to get the most power, well, that's a different mix than the one that saves you the most money on fuel. So right out of the gate, you're making a tough call. Are you going for raw power, or are you trying to save on costs? And wait, it gets even trickier, because that very same air-to-fuel ratio also controls what's coming out of your stack. If you run lean with too much air, you end up creating more NOx pollutants. But if you run rich with too little air, you get nasty stuff like carbon monoxide and unburned fuel. So just imagine being an operator, constantly trying to balance on this three-way tightrope between power, efficiency, and keeping the air clean. Okay, as if that wasn't enough, let's throw another wrench in the works. It's called tramp air. Basically, this is sneaky air that leaks into the furnace where it shouldn't be, through cracks, open peepholes, you name it. And here's the key. This air is useless for combustion. It doesn't help burn the fuel at all, it just gets in the way and dilutes everything. And this is why tramp air is so incredibly dangerous. Your oxygen sensor on the wall might be reading a nice high number, making you think, great, everything's safe. But what if that's all just tramp air? What if the burners themselves are actually starving for oxygen? You've created a ticking time bomb, a fuel-rich condition, and your instruments are giving you a false sense of security. It's a terrifying scenario. So to keep all of this under control, operators have some help from automated systems called control loops. You've got one for fuel pressure, making sure that's steady. Another one manages the flow of the product itself through the tubes. Then there's the draft pressure control, which uses the stack damper. And of course, the big one, the temperature controller, which is always adjusting the fuel to hit that perfect process temp. Okay, so day-to-day operation is complex, for sure. But nothing, and I mean nothing, compares to the risk you face during startup and shutdown. These are, by far, the most hazardous moments. And listen, that's not just my opinion. That's a hard fact known across the entire industry. Statistically, more things go wrong, catastrophically wrong, during light-off and shutdown than any other phase of operation.
This is where following the procedure to the letter is absolutely life or death.
Let me show you just how fast a situation can spiral out of control. So let's say the quality of your fuel gas changes suddenly. It gets a little richer. Okay, so more fuel energy is delivered to the burners. Now, weirdly, this can actually make the flame cooler, so the temperature at the outlet starts to drop. The automated system sees this drop and does exactly what it's built to do. It screams for more fuel. And just like that, you've created a terrifyingly fuel-rich environment that's just waiting for a spark.
So what's the right way to do it? How do you prevent that nightmare scenario? It all starts with a purge. You blast the whole system with dry steam to push out any flammable gas that might be lingering. Next, you double and triple check that all your safety permissives are good to go. But the most critical step, the absolute go-no-go moment, is getting that clear signal from your instruments, confirming there's nothing combustible left inside. Only then, and I mean only then, can you even think about lighting the pilots. You just can't take shortcuts here, ever.
All right, we've talked design, we've talked controls, and we've talked about those critical procedures. So now let's put it all together and see what good really looks like.
Okay, so if you're going to remember just a few things from all this, let it be these. First, know your draft type inside and out. Know what it can't and can't do. Second, you have to be constantly managing that tricky balancing act with the air-to-fuel ratio. Third, you have to always be on the lookout for tramp air, because it will lie to you. And finally, those startup and shutdown procedures, they are sacred. Treat them like the law, because they are.
Now, the really cool thing is that technology is giving us better tools to deal with all this. We now have these amazing tools like tunable diode laser spectrometers, or TDLS. They can literally look right into the hottest part of the furnace and give you real-time readings of both oxygen and combustibles right where the action is. It takes a lot of the guesswork out of the equation.
And that kind of brings us to a really interesting final question. As our instruments get smarter and the control systems get more and more automated, what happens to the human operator? Their job is changing, right? It's less about turning knobs and more about having this deep, intuitive understanding of the entire system and knowing why the automation is doing what it's doing. So I'll leave you with this. In that control room of the future, what do you think is the one skill that a human will always have that a machine never will?